headline of my presentation is Evaluating the Hydrocarbon Potential of Unconventional Reservoirs in Bangladesh. Let me start with 3 cautionary remarks regarding the hydrocarbon or energy scenarios in Bangladesh. As you know, we have 27 gas fields. All of these were identified in the conventional reservoirs through seismic and wildlife log data interpretation. Most of the fields are in the eastern part of Bangladesh. Among the 26 gas fields, now 20 gas fields are producing. So the present, regarding the present scenario, the State Minister for Power, Energy and Mineral Resources, Mr. Nusrul Hamid MP, told in the National Parliament that the volume of extractable reserve of natural gas is the remaining gas is only 12.54 TCF. This was announced in year 2018, but the total volume of recoverable hydrocarbon might be a little less than that amount. Professor Budrul Imam said that the present gas reserve in Bangladesh is 12 TCF, but 1 TCF gas is being used every year. So we are going to face the depletion of natural gas in the coming future. Since if we go in the same case, so it will be finished or might be dramatically reduced the pressure or depleted the pressure within 10 to 12 years. So energy experts and Buet Professor Tamims also said that the remaining recoverable natural gas is only 10 TCF. So the energy scenario in Bangladesh is not very promising. If we consider the conventional reservoir or the overt gas field scenario, so what we should do? So this is the main question right now. So if we think about why we are really concerned about this energy scenarios, if we look at the Human Development Index worldwide, you see Bangladesh have only in the index it's stayed around 0.6 in the median human development scenario. Though Bangladesh, you know, the natural development, national development seriously dependent on the uninterrupted power supply, and then most of the power is generated from the natural gas. So although the Bangladeshi people have the electricity consumption is low, but recently the access to the electricity increased dramatically to 97% in 2020. This is a good sign, but the continuous supply for the electricity heavily dependent on the natural gas supply. That's why it's very important for us to look for more natural gas. And if you look at the SDG goal, so you need access to affordable, reliable, sustainable, and modern energy for all. This is the SDG goal 7. So this is very important. So we should have the uninterrupted energy for our development. And then if you look at the scenario of the projection of the natural gas and the power development up to 2041, so you see the total amount of gas which will be used for electricity generation will be decreasing, even if we have a huge discovery in the coming future. But the real scenario is not like this. It's a more seriously, we are actually going a lack of pacing with the supply and demand. So we really have to focus on the production of natural gas in some way, or a nation cannot completely depend on the import-oriented energy or the natural gas. So what should we do now? Should we increase the exploration activities in frontier areas, develop existing gas fields, evaluate the potentiality of complex structures for conventional reservoirs, assess the potential of unconventional hydrocarbon reservoirs? These are the main questions. As you understand, the conventional reservoir, it's depleting very rapidly. And then most of the exploration was confined to the conventional so far, and very simplistic structure. So we really need to focus on the unconventional. As you understand, the world, if you consider the world scenario, the worldwide the conventional reserve is depleting. That's why lots of developed countries worldwide, they're focusing on the unconventional ones, and then few countries have very good results, even 4 to 5 times total reserve they have discovered in context of unconventional compared to the conventional one. So we really need to focus on the unconventional hydrocarbon reservoirs. This is the right time. So if you look at the unconventional gas in global context, worldwide, a lot of the nations, they are focusing, but Bangladesh, including India and subcontinent, and a lot of other countries are still lag behind in context of the world scenario. But what's British Petroleum Statistical Review of 2018, they have published this scenario that we have a huge potential in the Asia Pacific region. See, the most abundant, the highest possibility of the unconventional reservoir. So this is the main hope. So if we really focus on that point, I think this total scenario will be changed. If we look at the research triangle, as you see, the conventional reserves, these are I think you have seen this type of figure a lot of times. So main point is conventional reservoir is small, easy to develop, and then unconventional usually very large but very difficult to develop. It's not very easy. So you have to increase the pricing of the production cost or the market price, and at the same time you have to improve your technology to achieve or find unconventional reserves. So this is the main point. So if you look at the definition of unconventional and conventional one, the main point here is that the conventional is a discrete accumulation with map boundaries and distinct hydrodynamic realm. Sorry for the spelling. Unconventional, continuous accumulation in a wide area and not affected or separated by hydrodynamic realm. So as I mentioned in my earlier slide, that you need to have the increased pricing and then improve technology. So in unconventional reservoir, since Bangladesh occupy the parts of Bengal basin where the place is actually represent a gas-rich province. So if we look at the right leg of this triangle, so we should have look at the tight gas formations, thin bed reservoirs, and then the rest of the things we are not really ready to focus on. But I will also focus in my presentation the possibility of gas hydrates. The coal bed methane is a high ambitious project for Bangladesh, and the shale gas. This is also not very easy in Bangladesh, but from the geological point of view, it's not the right place for the shale gas in Bangladesh. Only few areas could be potential. So where should we, as I mentioned in my earlier slide, that we should focus on the thin bed reservoirs, tight gas sands, or the the definition of unconventional reservoir depends on your economy, your geological setting, your needs, and availability of technology. So there, in a sense of definition, so what we called as unconventional might be is conventional in other nations due to their available technology and their economic perspective. But anyway, so in our case, we will mainly focus to this in today's presentation, the tight reservoir and the thin bed reservoirs and gas hydrates mainly, or some stratigraphic traps as well. Although stratigraphic are sometimes considered, in most cases, considered as the conventional one. But still, since we are mainly focusing on the anticlinal structures or structural traps, so this is the right time to focus also on the stratigraphic traps. So where should we find the unconventional reservoirs? If you look at the earlier time scenario of the depositional environment in Bangladesh, the two scenarios has been presented here: in the late Miocene time and the early Miocene time. This is the paleogeography. So if you look at the fluvial, delta plain, delta front environments, so the geological environments, are really crucial to look for the conventional as well as unconventional reservoirs. It's very important. So how can we understand what should be the right place or right depositional environment to look for the unconventional reservoirs? In this context, if we consider the whole scenario in a way that we should focus to re-establish or revisit the stratigraphic or tectonosedimentation scenario of the then Bangladesh, so we should focus on the sequence stratigraphy, which will integrate the seismic, well log, outcrop data, core data, and modern modern analogy of the outcrops and the geophysical data. All this information you need to understand to find the unconventional reservoirs and their depositional environments. Very crucial. It's important. So if we look at the two more important geological formation, the Bokabil and Bhuvan formation. So if you consider in the Miocene time, the Bokabil, the upper lying formation in the Surma group, which is the most important hydrocarbon reservoir in which the most of the hydrocarbon reserves exist in the Surma group, the upper formation, the Bokabil, it will replicate, or it will represent the present day Magna estuary region, or the fluvial dominated delta system in the Ganges Brahmaputra Magna river system, this area, the Bhuvan, which might be representing the tide dominated delta system, the then Earth. And then if we look at, because it's a huge subject, the sequence stratigraphy, so we will just focus on a few slides. How should we go, or how should we find the right depositional environment and the right place to look at? So if we, I will just present only few slides to give some hints how we should look for the unconventional one. So if we see this seismic section, the whole stratigraphic scenario, if I revisit the TPAM, the which overlies the most hydrocarbon prolific group of the Surma, this is low stand in the context of sequence stratigraphy, where the system tract, and then Bhuvan represents the transgressive system tract, and Bokabel the high strength system tract. So this system, and then underlying the Oligocene or the boreal group represents the low strength system tract. It's a very simplistic way that the first order sequence, if we present it, but if we really go for the unconventional, we have to go for second order, third order, fourth order, even fifth order to understand the exact facies association for the unconventional reservoir. So you see the total seismic signature is different from the Bhuvan and Bokabel. They're the two different depositional systems these two formations represents. So if we start from here, and then we should go for second order, third order, fourth order evaluation of the system tracts or the sequence in context of depositional environment. So if you look at the well log information in the context of the previous slides, in comparison to the previous slides, you see the log signature also correspond very well with the seismic information. You see Bhuvan formation, which was transgressive, its log response is completely different from the low stand TPAM or the Oligocene, that means boreal group. But the high stand Bokabel and Bhuvan, these two are also different. So these are very preliminary studies, but you know, we have to be careful about the very simplistic and very simplified stratigraphic framework. But anyway, we should look at the unconventional reservoirs delineation or definition in the context of sequence stratigraphy. It's a huge part. I don't have any scope to go in detail in this presentation today. But anyway, so these are the very well-known cartoons, how the particularly the gamma ray signature of the log motif represents the different types of depositional environment. So if you look at this the cylindrical shape of the gamma ray, it's the aggregating depositional setting. The braided fluvial channel system distributed, all these. So these are not the unconventional in the context of thin bed or tight reservoirs. It's a very promising the conventional one. So if you look at the last one, that means which represent particularly flat plain, crevasse plain, sometimes delta plain, or the shelf margin, or in the deep marine like mid or delta fringe, fan fringe area, or the outer channel sheet structure. So this will be the type of log signature. So if you use the seismic, well log, core data, and outcrop analogy, so you will have a better and a clear understanding. So where to look at and how to interpret the unconventional. So this is the main point. So if I go a little bit, I think these are the cartoons you have seen several times. I shouldn't stay here a longer time. But anyway, the prograded delta system, and if you look at the delta plane particularly, or in the delta front, so you will find a coarsening upward sequence, and also the thickening of the sand, which are the possible reservoirs. And then the opposite scenario will be seen in the transgressive settings. So these are the points you have to keep in your mind to find or look at for the unconventional reservoirs. You see the sand shale alternations. These are the main point, because if you have a huge thicker sands and a good quality reservoir with a high porosity environment, this is conventional. It's already discovered gas in Bangladesh. It's already known, but in the previous exploration scenario, we mostly avoid this type of scenario. So we really need to look in this type of scenario from now onwards. these are also the similar things. And then the deep marine scenario. And then if you look at it's a crevasse place, you see there lot of sand shell alternations. And I have some field work, and then we have seen this sand shell alternation scenario of crevasse place of floodplain deposits or even delta plain deposits, which we should look for this one. Then there's the floodplain deposits, and then you see the lots of these dominated lithologies have the shale, and then occasional sand body will be encountered from the log data. And then in the same time, we are also showing the core data for comparison. And then if we look for the outcrop scenario, this is the northernmost part of Bangladesh. There's a huge section with sand shell alternations. It's very easy if you look at from a broad perspective. If you look at in a focused way, you see the ripples, and then the flazer type of bedding, wavy bedding, lenticular bedding. That means the facies association mostly found in the intertidal environment. And then this type of facies association, for example, if you have the sand dominating lithology, so this which will be representing the flazer type of beds, the reservoir quality will be relatively better than the wavy facies associations. So if you look also at this type of section, it's a good section with a sand shell alternation. Very easy. If you go and then drill it, you'll find hydrocarbon. It's not that easy. So if you look at in a focused way, you will see how complex the facies association, both in the vertical and then lateral point of view. So you are looking for the well log information, seismic information. But if you compare or deleted the geophysical data with the outcrop analogy, then it will be easier for you to take the next steps, how you should go to explore and then exploit if hydrocarbon is discovered in this type of scenario. And then what I have mentioned in my previous slides, that we have also seen some sand shell alterations. There's if you from the conventional point of view, if you have some reservoirs less than 1 meter or 2 meter thick, then you are not considering it's a conventional reservoir. So you have a number of sand layers with shale intervals, and the reservoir quality with these thin beds are almost comparable to the conventional reservoir with a good reservoir quality, with porosity permeability with a range of 15 to 25%. And then we have also seen this permeability is very good. So if you have if you consider the total vocabulary, for example, if it's 3 kilometer, and then if you reduce the total shale amount, the shale dominated amount, for example, if you consider the goin and vocabulary altogether, and then if you have like 6 kilometer, and then you subtract by 4 kilometer, then you still have the 2 kilometer with the sand shell alternation. So within 2 kilometer, if you consider net over gross of like only 0.3, then you have 600 meter thick total sand body. It's not a small one, it's a large volume. But the important point is whether these thin beds are hydrocarbon charged or not. And then the most important point is the reservoir quality in most cases in the thin beds are very good. But in other cases, when we have seen it's very tight, and then diagenetic changes make things even worse. The porosity permeability deteriorate dramatically. So it's not very easy. It's sometimes if you find this type of reservoir, it's good. So if you accumulate all the thickness together of the thin beds, it's a huge volume. So in the previous in the previous exploration scenario, they usually in most cases they avoid this type of reservoirs. But this is the time to look at these thin beds. So this is the southernmost part where we have seen a huge thick succession with sand and shale alternations. But if you look at in the closer view, so these are the scenario. So you see the porous media and then the impermeable shale portion of a silt shale, as it's and the lateral facies change is dramatic and also the vertical one. So this could be considered as a tight reservoir. It's not the thing, but this is completely different from the previous slide. See, so these are the just to have some idea what is the what the tight and the thin bed reservoir look like in the field. But in the seismic data, we will not understand very easily this lithology or the facies change. But there are some methods to make the facies model. You have to have a lot of information as input to make the facies model from seismic inversion. And then you can also find the tight or thin bed reservoirs using high quality, high resolution log data as well. But this outcrop scenario will give you some insight what the tight and thin bed reservoir look like. Here is the in the offshore Bangladesh one scenario. You see, as you remember, the Tipam, Bokawil, Bugon, and then the log signature also the similar what we have seen, the transgressive, high stand, and then low stand, the similar scenario. And then from this seismic, it's not very easy to understand. So where are the thin beds? Because you know the seismic resolution. You can go in the conventional seismics like 15 meter in the vertical resolution. So very difficult to find the thin beds or tight reservoir from the seismic alone. What I mentioned in my previous slides, that how diagenesis or how was the reservoir quality inside the rock, what we have seen in the naked eye in the field. If you look at under the microscope, so you see in the thin bed, sometimes the cementing materials totally occupy the pore spaces and the porosity reduced almost to zero. And some partial dissolution will produce some 2, 3, 4, 8% porosity. So you could consider this type of reservoir with a very little porosity and permeability as a tight reservoir. And then sometimes if you see the cementation, how it reduces the porosity and permeability of the reservoir. So until and unless you have the thin section, it's very difficult to understand. And then diagenetic effect there due to the compaction, the squeezing of the ductile particles, its flow along the pore spaces and pore threads and completely destroy the reservoir quality, grain bending, fracturing. And then you see this alteration of feldspar. It produces a lot of clay minerals. And then migration of fines, that means the migration of clay minerals with the pore water, it's reduced the pore thread diameter and then deteriorate the porosity and permeability dramatically. But these are all the negative aspects. But if you look at the rightmost slides, dissolution, oversized pore space, partial dissolution, and then you have a new porosity. This is the good results, good news. So the diagenesis not only deteriorate the reservoir quality, sometimes it's also enhance the reservoir quality. So if you have the clear understanding of the thin beds or tight reservoirs, then it will be very easy to take decision whether this layer could be considered as a thin bed or the unconventional reservoir or not. And then if you compare with the conventional one, thin bed reservoir and tight reservoir, if you the thin bed reservoir, the outcrop, thin section, and scanning electron microscopic scenario. These are interconnected pore spaces. You see that blue color dye indicate the interconnected pore space. It's a very good quality reservoir, although it's very thin. So if we consider this accumulated or cumulative thickness of these thin bed reservoirs, it could be like 400, 500 meter. But the question is, all the thin beds, if all the thin beds are charged with hydrocarbon or not? These are the vital questions. If you look at the Trite reservoir, the thin section, and then its porosity and permeability relatively less than the previous one, but you still have some connection. So you have to have a different approach to develop this type of Trite reservoirs, if there is any hydrocarbon. The thin bed reservoir analysis by the outcrop studies, what should we do? Logging is the intermediate frequency band which we used to study the subsurface, and seismic is the low frequency method. And core and outcrop is just the reality. So if we consider the wireline log data, it's a intermediate or medium frequency method. So depending on the log type, you can define the thin beds starting from like 2 to 4 feet in sonic and deep resistivity and 0.5 inch in micro images. So it depends on which log you are using to understand the thin beds. Because if you have the thin beds or tight reservoirs, the thickness less than 2 meter or even less than 5 meter, you will not consider it in the conventional point of view. And then it's sometimes very difficult to find because logs sometimes represent the average thickness, averaging the thickness and properties. Where you have like 3, 4, 5 beds, but the instrumental resolution is not that fine like the actual scenario in the field is. That's why the instrument will make an average of all the thin beds together, and then you will find a thicker bed in the response. So it depends on which log you are using. The three methods I usually use: the borehole image tool, resistivity anisotropy method, nuclear magnetic resonance NMR tools to find the thin beds. I'll not go very detailed of these tools, but I'll show some points how this works. So you see the conventional well log scenario and then the image log. It's very easy to understand the thin beds, but from the conventional it's very difficult. You cannot find this high resolution thin beds. The image log will help you to find the thin beds which might be averaged in the conventional log. Here is the analysis that means the resistivity anisotropy. When we consider the vertical resistivity, actually if you think about all the thin beds in a series arrangement, then you are actually calculating the vertical resistivity. But when you consider all the thin beds, the sand, shale, in a parallel arrangement, then you are measuring or estimating the horizontal resistivity. So if you have the sand shale alternations, and then you are calculating the horizontal resistivity, the value will be low because the resistivity in the shale is low compared to the sandstone. So if you have shale in the reservoir, the sand shale alternations, then the horizontal resistivity will be much less than the vertical one. So if you make a ratio, horizontal resistivity over vertical resistivity, you will find a prominent result of the anisotropy. So what this will give you? This will give you an insight whether there is a sand shale alternation of thin beds are there or not. So this resistivity anisotropy, I explain it in a very simple way, but there is a very good uh, workflow to understand or study this resistivity anisotropy. So the resistivity anisotropy is a very good tool to understand the thin bed reservoirs or study the thin bed reservoirs. And then the nuclear magnetic resonance. So this also make a much better and then even better than the image log, because it will not only produce the thin beds, and also the amplitude will give you the information about the lithology as well as the fluid content. Very good method. And then if you use this type of well logs, this is really helpful to find the thing that you see these tools, how fine resolution you can achieve from this type of logs. But the conventional, really difficult. The seismic spectral inversion. So, 1/8 of the wavelength is the fundamental limit of vertical seismic resolution. You will find only 1/8 of the wavelength vertical resolution will be. So what will happen if you have the less or the less thicker layer? So it will produce some tuning effects. That means it will amalgamate few layers into one and then make a stronger amplitude response. To overcome this, in this case, since I have mentioned earlier that seismic is an low frequency, comparatively low frequency method. So with a low frequency, you will not see the very thin layers. But if you have the wavelength or wavelength larger or low frequent, then you will have the tuning effects. To overcome this type of effects, the two person, Portia-Guin and Castanga, they have introduced a spectral decomposition and inversion method to resolve the thin beds. So this is very simple method, So if we consider that in that seismic acquisition, I have a frequency band from very low to high. For example, 10 hertz. Usually we use less than 10 hertz, for example, 5 hertz to 120 hertz data in seismic. So what this frequency band will do? High frequency will produce the fine tuning, and the low frequency will average these things. And then we'll have the tuning effect with high amplitude. But if you consider, or if you remove, not remove, but if you do not consider the low frequency data, that means you start with frequency from 25 to 60 hertz, for example, then the wide, then the full frequency band data will produce the high resolution seismic data. You see, here we will see only 2, 3 layer, and then here we have counted 8 layers. All the thin beds has been resolved. But there is a question, because if you do not consider the low frequency data, then your amplitude will be reduced. You see the amplitude difference upper and lower. So there is a trade-off. If you want to see the thin beds, it's in high resolution, then high frequency you can use. And then if you consider the whole full band of the frequency, then you have the high amplitude. So you have all the options. Both the options you can play around. But if you only use the high frequency data, there is a problem that you have the high resolution thin beds, but you will lose the gas effects. You will lose the high amplitude. So it's very difficult to differentiate. Or you will lose the direct hydrocarbon indicator options. So there should be a trade-off. which frequency you should use. It's better you use both way. You have the whole frequency band and then high frequency band. This is another example. I would become more, there's a higher resolution data. So you have also find the fine or thin bands in these cases. So using the seismic, outcrop, well log data, core. And then as you remember, I have started the sequence stratigraphy because sequence stratigraphy is a very vast subject. So you will find the appropriate or the accurate sedimentary environment. You understand the Pointberg signature and the floodplain signature will not be the same. And then the delta plane signature and the delta front signature will not be the same. That's why, or the fluvial signature and the deep marine responses of log or seismic will not be the same. That's why you must have clear understanding where you are looking. What is the depositional environment? What is the depositional setting? And then precisely you can understand using the sequence stratigraphy. It's a very good tool. Yeah. You will use all types of data here, available data to understand. And then in the fine tuning, you can use the proper logging tool, seismic inversion methods, and then outcrop analogy, course data all together to understand clearly. And then I have mentioned that I also will focus on the gas hydrate scenario. This is unconventional in the context of Bangladesh. We never started, even we didn't think about the gas hydrates accumulation in the offshore Bangladesh. The towed streamer EM electromagnetic method can be used to find the gas hydrates. So the main theme is here. So the electromagnetic wave will be generated, and this electromagnetic wave will propagate in all direction, and parts of the electromagnetic wave will propagate in the subsurface. So the response, or the return response, will be different depending on the interaction of the electromagnetic wave and the interfaces in the subsurface. If you have resistive layer, then your response will be stronger. If you have conductive, your response will be weaker compared to the background. So this is very simple method. If you have resistive gas hydrates, definitely high resistive compared to its surrounding. So if you have the gas hydrates, you will have the strong response from electromagnetic method. So this is very simple way. Simple, but it's the you know, the mathematical background and all the mathematics behind this method is not very simple like other geophysical methods. Okay, the method, if we just to make a little about this method, or those who are new to this method, I just want to make a little acquainted with this. So what? First, you have to have the acquire the data. Then you have make a QC and processing. This is the process data. This is a reservoir, for example. Over this reservoir, you see the stronger color represent a strong response. So over this reservoir, you have strong response. Very simple. So if you make a resistivity section and volume, then in the vertical section where you expect the reservoir, it produces the high response. Very simple. And then the inversion will also give the similar thing. So if you have the gas hydrates, usually gas hydrate produce just immediately below the seafloor, where you have the temperature range from plus minus 4 degrees. Then the gas hydrates will be frozen. Also, the gas will be frozen, interacting with the water, and then it will be preserved there. The main problem is the exploitation. Then if you want to exploit it, it will be evaporated and then go to the atmosphere. These are the main challenges. Worldwide, lot of companies, lot of researchers, academicians are trying to develop new methods how to extract the gas hydrates. Anyway, first of all, we have to discover whether there are gas hydrates or not in our offshore. The extraction and development is the next phase. Anyway, if you consider with the seismic and electromagnetic method. So if you see the seismic, the P wave velocity, and then an abscissa shows the hydrocarbon saturation. So hydrocarbon saturation starting from 0 to 100%. So you see the P wave velocity dramatically reduces up to 20% gas saturation or hydrocarbon saturation and then becomes stable. No change. So you will see very strong responses in this area, and then you could be misled that I have a huge gas here, but it's only 10 to 20%, and then you are completely misled. But in activity, then it's in logarithmic scale. See, logarithmic scale, and then it will gradually increases like with the saturation. So if you have like 70% saturation, so your responsible 10 ohm meter, it's 90% saturation, it will be like this 50 or 60 ohm meter. But if you have 20 ohm meter, say only 2 ohm meter, 20% saturation. So this is the beauty with the electromagnetic method. This represents clearly the saturation of gas, hydrocarbon. But sometimes seismic methods are inconclusive regarding the saturation. So if you have both the method integrated, then really good results. Because seismic will give you the structural outline and electromagnetic method will inform you about the fluid. So if you know the structure and what type of fluid inside the structure, then you are done. Very good, excellent. So 2 plus 2 is not always 4. I used to say it's might be 5, 6, even higher. So if you integrate this type of geophysical methods, you will have very good results. This is the main point. So you see, for example, I have the seismically interpreted structure, and then I have very strong responses of inside fluid. So I will definitely drill the well here, right? So I have a structure. Then this crystal part, this was interpreted from seismic. You have the closure here, but they are not strong responses. Here the good closure and then very strong responses to the electromagnetic, which directly correlated to the hydrocarbon. Very good. This is the place to drill to find the hydrocarbon. Here you also see. So this method could be used to find the gas hydrates. So I have made a very simplistic model, but patchy model. You know, in the gas hydrate scenario, it's not a continuous or in the crystal. It's a like a patchy model, and then it's not a solid body, so it could be patchy, and then it's a distributed sporadically below the subsurface. So if you make the model, and then we have some acquisition parameter. This model, for example, the resistivity of the air, it's more than 10 to the power 9 ohm meter, then water, seawater, 0.3 ohm meter background, and then high resistivity in the gas hydrates. So we have make this model. Then if we traverse with a vessel and then towed streamer behind this and produce electromagnetic wave, this will go in the subsurface and we'll have some receiver sitting here or behind the vessel. So the response will be really strong over the gas hydrates and will be weaker outside the gas hydrates. If you compare these two, you'll easily find or delineate the gas hydrates. So So if you do the model, these are the results of 400 models for Bay of Bengal scenario. And then in this model, so if you have the resistivity ranging from, for example, 25 ohm meter and higher, and then the water depth from 500 meter to 1400 meter, the water depth in the sea. So these the response threshold will be, you see, 1.1 means 10% increase, 1.20 20% in this way. So if you have the low water depth but high resistivity, of the stronger response. So these are the scenario. So if you run several models, like I run for 400 models here, and then if you normalize the response over the resistor with the response outside the resistor, that's the background response, then you will see the normalized response. If you have 10% increase with respect to background, then you can detect the gas hydrates. Okay. And then if you have only 5-degree deviation in the context of phase, then you also can detect gas hydrates. This is the modeling scenario. Now, if we see the EM sensitivity of changing resistivity and thickness, the thickness vary from like 25 ohm meter, and then it's 100 meter below the mud line, that means sea floor, and water depth is 1100 meter. Okay. And the target resistivity, the gas hydrate resistivity is 25 ohm meter. This is the model. And in this intersection is the threshold is above 625 ohm meter square, thickness multiplied by resistivity, control line. Then we should have sensitivity, the signal over the signal to noise ratio. Okay, then we can detect it even with a 25 ohm meter and then 25 meter thick gas hydrates can also be detected. So this is the modeling scenario. So if we run this acquisition, and I think within the water depth range, like less than 1000 meter. So if we increase the resistivity and then the thickness and resistivity, the threshold will be moving towards the greater water depth. That means for the minimum thickness and minimum resistivity, you can detect even under the within the range of 1000 meter water depth. But in the greater water depth, the sensitivity decreases. But in this case, you should have thicker gas hydrates and resistivity should also be high in the Bay of Bengal scenario. So I have come to my last slide. So what we have evaluated, re-evaluate the existing seismic well log and core data in context of sequence radiography to find where the theme bears. Because if you look at the gamma ray or sonic or resistivity log, you will have at least an idea what should you look for. And then you go for the image log, if available, or the NMR, or the spectral seismic decomposition and inversion, or the resistivity anisotropy. You can validate your data by outcrop analogy, and thin section microscopic and SEM study can give you some insight about your thin bed reservoir, which you have found or detected from outcrop or seismic or wildlife data. And then I have mentioned that these techniques can help you to determine the thin layers and use Mudlock responses. That means gas effects or gas shows, DST, etc., to So you have all the thin beds, but if you do not have the hydrocarbon charts, then it's useless. So you have all the drill holes available. You have the mud logs. You have the seismic well log data. You have lots of outcrops. So what are my suggestion? Not for this audience, but the responsible people, because they have the mud log, they have DST, all this information they have. So they first determine the thin beds and then use the mud logs information, and then very easy to detect where the thin beds, tight reservoir, or from the sequence stratigraphy, even the channel cut or pinch out stratigraphic reservoirs. And then definitely if you use the CSM to find gas hydrates. These are the points or the slides today I have to present in front of you. Thank you very much for your attention.